A single number broke physics, and it's not P, not E, not infinity. It's 10 to the 120. If that looks like a throwaway, think again. This is the size of the mismatch between what our best theories say the energy of empty space should be and what the universe actually does. Tonight, we'll unpack why emptiness has energy, why Einstein's equations care about it, how quantum fields blow the prediction into absurdity, why just cancel it isn't a solution, and the handful of escape routes physicists are still exploring, from supersymmetry and sequestering to cosmic selection effects and the holographic edge of the universe. By the end, 10 to the 120 won't be a meme. It'll be a map of where our understanding stops. Start with the punchline. The universe is accelerating. Distant supernovae grow dimmer than they should be in a decelerating cosmos. The cosmic microwave background and the way galaxies cluster agree. The simplest way to describe this is to add a constant term, L, to Einstein's field equations, an energy density of empty space that doesn't dilute as the universe expands. In ordinary units, L is tiny, about 10 to 52 per square meter. In energy density, that's roughly 6 by 10 to 10 joules per cubic meter. So little you'd miss it in a box of air. In natural Planck units, where you measure everything against the scales set by quantum gravity, that same density is 10 to 120. That's the famous smallness. The observed vacuum energy is 120 orders of magnitude below the naive quantum estimate. Flip the ratio and you get 10 to the 120. That is the number that broke physics. Now, why does empty space have any energy at all? Because in quantum field theory, fields are everywhere and never perfectly still. Each mode of a field, a way it can vibrate, carries a zero-point energy of 1 hu. The same way a quantum harmonic oscillator can never be completely at rest. Add up all the modes and you get an infinite sum. In ordinary particle physics, you shrug and subtract it away. Only differences in energy matter for scattering and decays, and your detector can't see a constant offset. But gravity is different. In general relativity, energy tells space-time how to curve. A constant energy density is not just a constant. It is precisely what L is. Gravity cares about the absolute level. So you try to be careful. You regularize the infinite sum by cutting it off at some high frequency where you think your theory should stop applying, maybe at the Planck scale where quantum gravity takes over. The result is roughly cut off to the 4th power. If your cutoff is the Planck energy, the answer is 1 in Planck units. Observation says the true answer is 10 to 120. If you're more generous and pick a smaller cutoff, say at the energy where the electroweak force breaks, 1 trillion electron volts, you still overshoot by 60 orders of magnitude. Even contributions from known physics, like the binding energy of the quark-gluon vacuum in QCD, hundreds of MeV, would, on paper, give a vacuum energy density 10 to 45 orders of magnitude larger than what we see when we look at the sky. That's not a rounding error. That's a catastrophe. At this point, the natural instinct is to fix it by hand. Add a bare cosmological constant to Einstein's equations and fine-tune it so that it cancels the quantum zero-point terms almost exactly, leaving the tiny residue we measure. Mathematically, you can do that. Effective field theory is full of counter-terms that absorb infinities. The problem isn't that you can't write the term, it's that you have to tune it to cancel 120 decimal places and then tune it again after every phase transition in the early universe. When the Higgs field settled into its non-zero value, it shifted the vacuum energy. When QCD confined quarks into protons and neutrons, it shifted it again. Each time, your cosmic bookkeeper has to retune L to 120 digits to keep today's tiny value. That's not just ugly, that's unstable. Any small change in the high-energy theory wrecks the balancing act. Naturalness, the idea that small numbers should come from protective symmetries, is screaming. Could a symmetry save us? Supersymmetry tries. In a supersymmetric world, every boson has a fermion partner and vice versa. Because bosonic and fermionic zero-point energies come with opposite signs in the math, they cancel mode by mode. Beautiful, except supersymmetry, if it exists, is broken. We haven't seen superpartners at the energies we've probed, which means the cancellation is at best partial. Break Susie at, say, a few TeV, and the leftover vacuum energy is around TeV4. Still about 10^60 times too big in Planck units. Better than 10^120, yes. Still a disaster. Maybe vacuum energy isn't constant. Maybe it's a dynamical field that slowly rolls. A quintessence that mimics dark energy today, but could evolve. That idea avoids the worst fine-tuning by replacing a number with a function. But the function needs to be exquisitely flat, so the field hasn't rolled much in 13.8 billion years. Its mass has to be astonishingly small, like 10^33 eV, so it hasn't moved, and it must barely couple to regular matter, or it would show up in fifth force experiments. You've traded one set of extreme tunings for another. Observationally, the equation of state of dark energy, how its pressure relates to its energy, looks like W1 to within a few percent. A true cosmological constant has exactly UC to 1. Quintessence has to hide right next to it. What about modified gravity? Change the left-hand side of Einstein's equations, fiddle with curvature terms, add extra dimensions, give the graviton a mass, and perhaps vacuum energy doesn't curve space the way we think. There are serious, sophisticated theories here. FR gravity, where the action is a function of curvature. Massive gravity and its cousins, where gravitons acquire a tiny mass. Brain worlds, where leakage into higher dimensions weakens gravity on cosmic scales. Many of these models can reproduce acceleration. Many also face ghosts, instabilities, or fail precision tests in the solar system, unless they add screening mechanisms that conspire to hide modifications where we've checked and revealed them only in the deep cosmos. Even when you can get acceleration, the original 10^120 question often sneaks back in. Why is the vacuum energy small in the first place? There are also clever rewrites of the rules that target the bookkeeping problem directly. Unimodular gravity forces the determinant of the metric, a measure of space-time volume, to be fixed. In that setup, vacuum energy drops out of the equations of motion, and L appears as an integration constant. It's a neat trick, but it doesn't tell you why the constant takes the observed tiny value. It just moves the y one step sideways. Sequestering mechanisms go further. They add global terms to the action that, when you vary them, dynamically cancel vacuum energy contributions from matter fields, leaving L insensitive to high energy details. In toy models, sequestering works. In full quantum-consistent theories, it's still a battlefield. If you ever hear that someone solved the cosmological constant problem, ask whether their fix stays stable as you turn on loops, phase transitions, and gravity itself. There's a more radical answer you'll see attached to string theory and the idea of a landscape of possible vacuum states. Instead of one unique low-energy world, the theory might allow an enormous number of metastable vacua, different ways to curl up extra dimensions, different fluxes threading the geometry, each with a different effective L, different particle spectra, different microphysics. The number of distinct vacua quoted in the literature is ridiculous. 10 or 500 is a mascot, not a precise count. But the point is huge. If the cosmos ever samples many of these vacua, through eternal inflation, say, then most regions would be sterile. In regions where L is too large and positive, the universe blows itself apart before gravity can gather matter into galaxies and stars. Where L is too negative, expansion halts and everything recollapses. Somewhere in the sliver where structures can form, observers can evolve and ask questions. Steven Weinberg turned this into a quantitative argument in the 1980s. He computed an upper bound on L from the requirement that galaxies form and noted that our measured value is close to that bound. This is the anthropic move. You don't derive L from first principles. You explain why it's not bigger or smaller by selection bias. To some physicists, that's sensible given the data. To others, it's a surrender flag disguised as a prediction. Why is this such a sharp problem at all, beyond the aesthetics? Because we know zero-point energies are physically real in other contexts. The Casimir effect, an attraction between conducting plates that's been measured with exquisite precision, can be computed as a shift in vacuum energy when you change boundary conditions. Superconductors, semiconductors, and lasers all feel the quantum vacuum in ways we harness every day. You can subtract away a constant in a non-gravitational problem and only care about differences. Gravity doesn't offer that escape. If the vacuum pulls on space-time at all, its absolute value matters. A common misconception is that a more complete calculation will make the zero-point sum exactly zero, so the problem goes away. But even if you choose a scheme where you cancel the quartic divergence elegantly, you can't escape the finite contributions from known physics. When the Higgs field picks a vacuum expectation value, it lowers the energy of the vacuum by an amount related to the shape of its potential. When QCD breaks chiral symmetry, the quark condensate contributes its own negative slice. Each of these is enormous in absolute terms compared to the astronomically tiny number we infer from cosmology. You aren't balancing infinity against infinity. You're balancing huge finite terms against a tiny residual. And because radiative corrections shift those terms whenever you change the energy scale, your balancing act is not set once and forget. It's set and reset, unless something deeper protects the smallness. There's a second, quieter puzzle sitting next to 10(120) that people call the why now problem, or the coincidence problem. Right now, in cosmic history, the density of dark energy and the density of matter are within the same order of magnitude. Billions of years ago, matter dominated. In the far future, dark energy dominates completely. Why do we live in the brief sliver where they are comparable? In LCDM, the vanilla model of cosmology, this is just a fact of timing. There's no mechanism that ties the two together. In some dynamical dark energy models, you can design tracking behavior so a rolling field stays comparable to matter for a long time, then takes over. But with current data favoring W close to 1, you can't track too aggressively without getting caught. The coincidence doesn't break the theory. It just adds to the sense that something about the whole picture is perched on a knife's edge. Let's zoom out and ask what 10-120 might be trying to tell us philosophically. Our best tested theories, quantum field theory for particles, general relativity for space-time, were never designed to talk to each other about everything. They overlap beautifully in regimes where gravity is weak and quantum effects are small. They fight in the ultraviolet and the infrared, at the highest energies where space-time itself should be quantized, and at the largest scales where tiny energies integrated over cosmic volumes move galaxies. The cosmological constant problem is a sign that the way we count energy and the way space-time counts curvature are not yet friends. Either gravity must somehow ignore most of the vacuum energy, or our bookkeeping for vacuum energy in the presence of gravity is missing a line item. That's why you'll hear proposals that sound at first like heresy. Maybe vacuum energy doesn't gravitate at all, only excitations above the vacuum do. But then you must rewrite the Bianchi identities, the conservation law baked into Einstein's equations, to permit that exception without breaking the rest of physics. Maybe gravity is emergent, like sound waves in a crystal, and the cosmological constant is like a pressure that gets absorbed by the medium. This is the flavor of some entropic gravity and holographic approaches. Maybe the value of L is set by global constraints on the whole universe, not by local physics, a boundary condition rather than a parameter. Each of these ideas carries risks: non-locality that's hard to contain, violations of energy conditions that feed instability, or conflict with precision tests. But in a field where add a counterterm failed to ease anyone's mind, creative pressure is a virtue. There's also a curious, possibly meaningful numerology that circles 10-120. The de Sitter entropy, the maximum information you can store in a universe with a positive cosmological constant, scales like the horizon area in Planck units, S3P-L. With our tiny L, that's about 10^122. Seth Lloyd once estimated that the total number of logical operations the observable universe could have performed since the Big Bang is about 10^120. In Planck units, the age of the universe is 1060. Its Hubble radius is 1061. Square those and you flirt with 10^122 again. None of this solves the problem. It just whispers that 120-ish powers of 10 keep showing up when you compare cosmic scales to the Planck scales. Whether that's deep or a coincidence is an open question. We should be honest about where data point. Multiple independent measurements, supernovae, the cosmic microwave background, baryon acoustic oscillations, weak lensing, converge on a universe that looks, for all the world, like L plus cold dark matter, LCDM. The effective pressure-to-density ratio of dark energy is very close to 1:1, with no strong evidence of evolution so far. Constraints on modified gravity from gravitational waves, which move at light speed to exquisite precision, and from the growth of structure are tight. None of this forbids new physics, it just narrows the lanes. If dark energy is a field, it hides near the behavior of a constant. If gravity is modified, it hides very well on the scales we've tested. So what would an actual breakthrough look like? One path is experimental. Measure the Higgs self-coupling more precisely at a future collider to map the shape of its potential. A different shape could change how we count vacuum contributions. Push precision on the top quark mass, Small shifts propagate to high energies via renormalization group equations and can tilt the stability of the electroweak vacuum. Hunt for ultralight scalar fields with exquisite fifth force experiments. Detection would put a new player on the board for cosmic acceleration. Build surveys that can distinguish W-1 from W-0.98 at high significance, and look for subtle anisotropies or time variations that would betray dynamics. On the theory side, tame sequestering in a fully quantum context. Find a consistent mechanism that makes vacuum energy radiatively stable, insensitive to high energy shifts, without killing the rest of particle physics. Show, not say, how holography works in a universe with positive L de Sitter holography is far less mature than its negative L cousin in anti-de Sitter space. Let's ground this in an analogy that doesn't insult your intelligence. Imagine you inherit a perfect clock that keeps time by a pendulum. You notice it's running fast by a tiny amount, 1 second per year. You open the case and discover the pendulum rod is made of a material whose length naturally fluctuates, but the escapement has been shimmed to compensate to 1 part in 10^120. Every time the temperature changes, a new shim appears that cancels the shift to 120 decimal places. That is what the just fine-tune L proposal amounts to. No watchmaker would accept it. They would look for a symmetry that locks the pendulum's length, or a design that makes the period insensitive to length, or a mechanism that sets the period globally rather than locally. That's where physics is, looking for a design principle that makes small l natural, not staged. One more subtlety before we land the plane. Even if you solve the smallness problem, you'd still have to explain why L is positive, not 0 or negative. A negative cosmological constant would make space-time curl inward, left to its own devices. A universe with all NLT, 0 recollapses. Zero cosmological constant would give you a critical, coasting cosmos that expands forever but decelerates in a specific way. We live in a gently accelerating universe instead. That detail rules out entire classes of elegant models and keeps the target pinned. Here's a cleaner way to hold the whole story in your head. The cosmological constant problem has 3 parts. The large problem, quantum fields predict enormous contributions. The radiative stability problem, even if you set L small at 1 scale, quantum corrections blow it up again. And the coincidence problem, why now? Any credible solution has to touch all 3. Supersymmetry helps with large, fails on radiative stability unless it's unbroken. Quintessence dodges coincidence with tracking, but struggles with data. Modified gravity plays judo with large by changing how gravity reads vacuum, but risks conflict elsewhere. Anthropic selection dodges both with a shrug and a bound, but leaves many scientists unsatisfied. Sequestering, unimodular gravity, and emergent approaches punch at radiative stability from different angles. The landscape of ideas is as broad as the number 10^120 is tall. If that feels bleak, remember where cosmology was 30 years ago. We didn't know the universe was accelerating. We didn't have a Higgs boson in the lab. Gravitational waves were a dream. Today, we can watch black holes merge, map the afterglow of the Big Bang with multipole precision, and trap single quantum systems that behave the way textbooks promised. The cosmological constant problem is not a sign we should give up. It's a sign we've reached the edge of 2 great theories and need a third story that includes both as parts. When physicists say, The vacuum is the most interesting thing in the universe. This is what they mean. The structure of nothing is doing the heavy lifting. Let me give you a dinner table summary that doesn't insult the details. Quantum fields say empty space should have a huge energy. Gravity says that energy should curve the universe. Observations say the curve is there but incredibly gentle. You can write down a constant that makes the numbers fit, but the tuning is obscene and unstable under the normal rules. Every fix we've tried buys clarity at one price and loses it at another. Somewhere in that balance sheet is the new physics we need. And a final picture to leave you with. Think of the universe as a stage. The actors are particles and forces. The script is the standard model. The lighting and scenery are general relativity. The cosmological constant is the tension of the stage itself. If it's too tight, the stage snaps and no play happens. If it's too loose, nothing holds together. Somehow, we live on a stage whose tension is tiny but non-zero, tuned to support structure for billions of years. Calling that anthropic is one way to cope. Finding the hinge that sets the tension is better. That hinge is the mystery behind 10-120. So yes, 10-120 broke physics. But breaking points are where new bridges get built. The number that looks like a failure today is the signpost that says, turn here. If you want to know where the next big idea in fundamental physics will come from, keep one eye on galaxies and the other on the vacuum between them. That empty space is not empty, and the smallness of its energy is the loudest whisper we've ever heard.